Hello everyone and welcome to my talk, Hyperinflation Stuck in the Swampland. My name is Bounakis and the work presented here is part of a research project carried out in collaboration with my supervisors, Ian Moss and Gerasimos Rigopoulos, as part of my doctorate degree in Newcastle University. Let me start by giving you a short overview of the talk. After a quick glance over single field slow roll inflation, I will briefly present and motivate hyperinflation as a cosmological model. Furthermore, I will be reviewing the background and perturbation dynamics, and I plan on providing some observational constraints for the model. I will end by providing some directions for further work. So inflation was originally motivated by the so-called zero-order problems of the cosmological standard model, and offers a mechanism through which primordial quantum fluctuations are stretched out of the horizon and see the observed large-scale structure. In the simplest models, a single scalar field slowly rolls down its potential, which is required to be flat enough so that the inflation epoch lasts for the required 60 or so e-folds. The model is very successful and is in agreement with observations. A reasonable question then becomes, why bother with multiple fields? First of all, the existence of a scalar multiplet is more natural than a singlet from a particle theory viewpoint. Furthermore, multiple field models have a richer phenomenology and might even come to resolve the tension between inflation and the Swampland conjectures. Lastly, multi-field models can provide very interesting non-Gaussianity signatures. So there's enough motivation for us to start thinking about multi-field models. As already discussed in the previous slide, the required number of e-folds is obtained in the single field slow roll case through the flatness of the inflaton potential. However, if the field space is not one-dimensional, but it is a two-dimensional and flat, a retarding force, for example, a centrifugal force, can assist the slow rolling, and therefore steep potentials can also be considered. This is the case, for example, in spinflation, in which the field orbits the bottom of its potential until it has lost its angular momentum. It has been shown, however, that the delay provided through this mechanism is insufficient, as velocities redshift and the angular motion quickly becomes irrelevant. A similar idea in which this regime has been placed in the hyperbolic two-dimensional space instead of a flat one, a space with curvature scale MH, has been proposed relatively recently. Now, the field space angular momentum can be exponentially large, and therefore the angular motion is relevant throughout inflation, providing the required number of e-folds. Since it is this field space angular momentum that is delaying inflation, the perturbations are adiabatic and almost scale invariant. This approach has been argued to result in a Hubble flow parameter of order close to 1, allowing inflation to maybe even evade the swampland. Let me then set the stage for you. After rescaling the fields by the hyperbolic space curvature scale MH, the action looks like this, with G mu nu being the FRW metric and GAB being the field space metric, where in the large field limit, the field space metric function f of rho can be taken to be an exponential. Power law potential hyperinflation is observationally excluded. So we choose an exponential potential that preserves the isometry of the field space metric. We can then transform into a coordinate system with unit vectors parallel and normal to the killing direction, and observe that the equations of motion then result into an autonomous system. We constrict ourselves in the zeta space by constraining the field space curvature scale to be a lot smaller than the Planck mass. With these considerations, we can turn to scaling solutions, solutions with epsilon prime being 0. One such solution for the autonomous system is the gradient one, in which there is no angular velocity and the radial velocity takes on this minus p rho value. Then we can calculate the local Lyapunov exponents, and depending on the potential parameter p, the solution is either a stable one for p smaller than 3, and then the field rolls down a radial trajectory while the angular velocity vanishes exponentially, as you can see from here. Or an unstable one in which the angular velocity increases when p is larger than 3. And you can see it here in the plots that as I increase this potential parameter p beyond 3, the gradient solution becomes unstable and the system evolves into the hyperbolic solution that we will see in the next slide. You can see here that, for example, in the phase diagram here for x being minus 2.3, you can see in the little dot there that the gradient solution is the one that is being followed, and here also. But when p is larger than 3, any non-trivial angular velocity will destabilize the system from the gradient solution into the hyperbolic one. Another solution is the hyperbolic one. The system here evolves in a spiraling motion. This solution of the system is only valid when p is equal or larger than 3, so that the positivity of the square root argument is ensured. Obtaining the local Lyapunov exponents, it is evident to see 3 distinct cases. One is when p is between 3 and 3.375, where the eigenvalues are both different, real, and negative. And then the critical point is a stable node. A second case is when p is exactly 3.375, when there is one single eigenvalue, minus 3/2, and the critical point is an improper stable node. Lastly, when p is larger than 3.375, there exist 2 complex conjugate eigenvalues with negative real part, and then the system spirals towards the stable focus critical point. I can now combine the 2 solutions, and we can see manifestly that for p larger than 3, the gradient solution is unstable, and any non-zero initial angular velocity of the system then evolves towards the hyperbolic solution here. And this makes it evident that the hyperinflation is an attractor in the regime that the gradient solution is a repeller. Now, having obtained the dynamics of the background, we can take a heuristic look at the perturbations. By taking 2 trajectories, a fiducial one and one perturbed from it, we can take the difference of the fields as they evolve. We expect from the plot here that the adiabatic, the one that is along the direction of the trajectory, will asymptote to a small constant, while the isocurvature or entropic ones that are normal to the trajectory will vanish. So let's try to see if this is true numerically. First of all, it is in general well advised to switch to a local orthogonal basis. By defining the adiabatic and entropic directions using these unit vectors. And we can observe that the Zweibein transformation matrix is a simple rotation in field space. Changing then the time variable to this z here, where we define this case star to be the wavelength of the mode that exits the horizon at time t, we obtain the equations of motion for the perturbations and note the highly non-linear nature of them. In order to be able to solve them, we initialize by making the ansatz that deep inside the horizon, the modes are decoupled and unaffected by the field space curvature induced mixing, and therefore the modes are given by the standard one-dimensional result that includes the Hankel functions. Having obtained the evolution of the modes, we observe that as y increases, the modes reach their respective asymptotes a lot faster, resulting in a spectral index that is well beyond observational bounds, and therefore we choose to restrict ourselves to y smaller than 1. And obtain the power spectrum of both the adiabatic and the entropic perturbations, the former of which approaches its asymptote, and the latter, as you can see, quickly vanishes as one approaches the end of inflation. Utilizing the measured value of the spectral index, the permissible values of the parameter y of hyperinflation models are tightly restricted. So you can see here that for the measured value, we are restricted to y being either 0.8 times 10 to the minus 2 to 10 to minus 2, which is this small region here, or 0.16 to 0.19, which is the region here. The tensor to scalar ratio, which is observationally bound to less than 0.1, restricts the exponential potential parameter, which in turn restricts the permitted values of the Hubble flow parameter to less than 5/8. Despite this being far closer to the required value than standard single field slow inflation, it is still in contradiction with the Swampland de Sitter conjecture, which demands that it should be order of 1. We are therefore led to proclaim that hyperinflation is still stuck in the Swampland. Before closing, let me recap and motivate further work. So we obtained the background and perturbation dynamics and investigated the cosmological implications of the exponential potential hyperinflation model. However, there is a lot more to investigate. We already have carried out some preliminary work in which we focus on 2 and higher order point functions, utilizing the stochastic technology, aiming towards the investigation of the implications and the formulation of stochastic hyperinflation. As a teaser for that future work, I offer here a plot of an initially Gaussian-like distribution of field configurations bounded by 2 neighboring trajectories. And as you can see, they evolve into something that appears to adopt a non-Gaussian signature. And with that, I would like to thank you for your attention